Okay. So as we talked about last time, I think like the beginning, I should probably share my screen. Yeah, so in the beginning, today, what we're going to talk about mainly is how to compute some tangent spaces. So I'll go over like the two examples we went over last time. I'll do them again, just so it is fresh in your mind. Um, and after that, we'll talk about. So before the break, we talked about um, like vector bundles and how to construct vector bundles through, a representation of a group and how you get like something called a cocycle, which then allows you to define a topological space that turns into a manifold and a vector bundle over that manifold. Um, but the thing is, um, that construction is very abstract. Um, and in reality, there's not much you can really, you know, um, do with that unless you have specific examples, So the one of the biggest questions one might have is like, why did I even introduce these notions if they never show up? Right? So what we're going to talk about for the rest of the meeting are just like these associated so we're gonna take the tangent bundle and see how we can move the like representations around to then talk about um other vector bundles on the manifold that show up all throughout physics. Okay. I don't know how much we'll be able to talk about because I do want to keep like a certain time constraint. Okay, so let's just begin with the computation of the tangent spaces. So let's um, to recall, remember that f of x, so from Rn plus 1 into R, given by, um, I guess I can make this a little, R given by f of x equals x squared, is smooth. I mean, this follows relatively quickly. Um, just from, if you take the derivative, you see that this will be smooth. Um, okay. What this means, oh yeah, the smooth uh, and is a submersion. Submersion. So if you remember, a submersion was a map whose differential at each point is surjective. And the reason we have to exclude the point zero is because at zero it is a critical value. Zero is a critical value because we have a minimum of this function at that point. So the derivative vanishes, and so it's not surjective. This means for all x in for all r in its domain, which is actually r bigger than zero, we have S n of r, which is f inverse of r, is a smooth submanifold. Okay, so I mean, this is what the regular level set theorem was, um, and these these level sets are precisely spheres of radius r, right? That's sort of built into this definition. It's like you're looking at all points away, like all points that have a distance r away from the origin, and that's clearly a sphere of radius r. So this is one way of checking that spheres of radius are actually, smooth manifolds. Um, without having to compute explicit charts or anything like that. One drawback of this is now you don't have charts, so it's hard to do, calculus on it. Um, but on the other hand, we saw that the tangent space, TP, S, N, at R was nothing but the kernel of the differential at the point. Um, and so we'll now use these we'll use this to compute the tangent space at a point P. Okay. So let's compute df at P. Remember, this goes from Rn plus 1 into R. Um, and now you might ask me, okay, like why is it like that? And why is it Rn plus 1? Because the tangent space at any point of this space is just Rn plus 1. Well, it's isomorphic to Rn plus 1, but you get the point. Um, what this means now is we can just compute it directly. So note that df at P is nothing but, so if you take the derivative of this thing, evaluate it at P, you get 2P1 up to 2Pn plus 1. Um, right? Which then means, so V is in TP Sn of R, um, and this is a subset of Rn plus 1, if and only if, um, so this implies that if and only if d df at P of V is equal to 0, which is true if and only if um, 2P dot V is 0, which means that P dot V has to be 0. Okay, P dot V equals 0. Right, and this gives you the description of the tangent space at a sphere at any point. It's just, the orthogonal complement of the span, and like you shift it up to the point P. Which should make sense, I think, right? Because um, we saw in like the textbook, sorry, not textbook, we saw in a homework exercise that a curve on the sphere, its velocity vector is orthogonal to the direction of motion. And we also know this from like Newtonian physics, where if we have, constant rotational motion, its acceleration is parallel to the motion, and its velocity is perpendicular. Right? So it's glad to see that it's good to see that at least okay. In the specific cases we know, what we've derived makes sense. Are there any questions on this? Okay, good. Um, so now let's move on to the tangent space of the orthogonal groups. So now let A be in the orthogonal group. And if you remember, A was in the orthogonal group if and only if A transpose AG equals G, where G is, the metric of signature PQ. Um, okay. Now, if you recall from the definition of a tangent space, the way we defined tangent vectors was we looked at velocity vectors through the space, right? And then we looked at, we looked at the derivatives of these curves at the point. So now the idea is we will take a curve in um, GLNR, um, and in a small enough neighborhood, and we'll see what condition we have to give on this point on this direction for it to be tangent to this. Um, so if you recall from last time, actually we don't even need to do that because last time, actually let me not write it as that. Note that OPQ is equal to F inverse of G, um, where F at A was A transpose GA. And we showed that um, dF at A was nothing but A transpose GX. Sorry, the derivative at X was A transpose GX plus X transpose GA, right? And the way we did this is we took the curve gamma of t equals a plus tx. So note gamma of 0 is a and gamma prime of 0 is x. And then you just put it into the definition of df at x and you get this out. This means that T of the orthogonal group um, is nothing but the kernel of df at A, which means it's the set of all x in GLNR. Sorry, it's the set of all matrices Rn squared. Um, I guess, yeah, Rn squared, which is equal to the matrices, like n by n matrices, such that A transpose GX plus um, X transpose GA equals 0. Okay. Are there any questions about this computation? Okay. Um, okay. That's for the orthogonal groups, right? So again, if you remember, we don't really care too much about the orthogonal groups, but rather we care about, the special orthogonal groups. And in the case of um, like Lorentz transformations, we care about the restricted Lorentz group, which is the restricted orthogonal group to the identity connected component. So, so essentially, um, this doesn't cut it, right? Because sure, we have the tangent space for the orthogonal group, but we actually care about a submanifold of the orthogonal group rather than the orthogonal group itself. Um, and so now we need to find a way to compute um, the tangent space of the special orthogonal groups. Um, but I will leave that computation up to you, and you'll see why. Um, I mean, it follows relatively quickly from the computation we'll just do. Okay, so now let's compute. Now let's compute the tangent space at identity of SL and R. And this is sometimes called SL, like SLN. Okay. Um, but I'll reserve this name for now. Um, this one is if you remember the Lie algebra. So if you remember what the Lie algebra of a Lie group was, this is actually the Lie algebra of the special linear group. But one thing we require for the Lie algebra was a bracket. We needed a Lie bracket. So that's why I will not call it SLNR for now. I'll stick to this, and then when we define the Lie bracket on it, I'll switch to calling it this. Okay. So if you remember, SLNR is the group of um, unit determinant matrices. Um, and so in spirit, it's very easy to compute what the tangent space at identity is because we just, have to take the kernel of we just have to take the kernel of the determinant map. Um, but I mean, and that's exactly what we'll do. So um, from exercises. So if you remember, I think in like problem sheet 2, I actually assigned this question. So from the exercises, Note that the derivative of the determinant function at identity of a point A is nothing but the trace of A. And I outline like the proof of this in the problem sheet. So this means the tangent space at identity of SLNR um, is just x in GLNR, actually in R squared, sorry, um, such that the trace of x is 0. Yeah. So it's just this set of traceless matrices. Um, and an exercise for you is to compute the dimension of this. I mean, you should, I feel like you should be able to see very quickly what the dimension of this space should be. One hint I'll give you is that the trace is linear and you can use, linear algebra to tell you the dimension as a vector space of this thing. And then you know, you could also just use the fact that SLNR has dimension n squared minus 1 to get you that this thing has dimension n squared minus 1. But I want you to like actually, check it because we know the dimension of this. Um, okay. So I've just computed the tangent space at identity for SLNR. And now one might ask me, okay, how do I compute um, the tangent space at other points? Okay. How do I compute the tangent space at other points? Um, and you could, find the derivative of the determinant at the other points and then, take the kernel of that map. Um, again, I've outlined how to take the derivative of um, the like determinant at other points um, as well. But we will not use that. But I wanna introduce like something, more powerful. So recall that excuse me, SLNR is a Lie group. To convince yourself of this fact, matrix multiplication is nothing but is just a polynomial in the entries of the matrix. Right? Each entry is just a polynomial in the entries of the matrix. So each component function is smooth. And then convince yourself that if each component function is smooth, then the function itself is smooth. Um, okay, that's matrix multiplication. Inversion, you can use Cramer's rule to also show that it's like each component is just given by some polynomial in the entries, and you're done, right? You've shown that it's a Lie group. Um, Now we will harness the power of a Lie group to note the following. So LB from SLNR into SLNR given by A maps to BA is a diffeomorphism. The fact that it's smooth just follows from the fact that multiplication by a matrix is smooth. And then it's a diffeomorphism just comes from the fact that this map is invertible with inverse LB inverse. Okay. So LB equals LB inverse composed LB. It's just the identity on SLNR. Um, this means um, the tangent space at B of SLNR may be thought of as the image of DLB of the tangent space at identity, right? Because I have a diffeomorphism, I guess one might have to check that this map is an isomorphism of vector spaces, but this follows from the chain rule and the, I guess, inverse function theorem. But you don't really need inverse function theorem. This follows from chain rule because you know that its inverse is smooth because it's also given by left multiplication. So by composing it, you get something. Okay. Um, and so yeah, it's all you have to do is once you know the tangent space at identity, all you need to do is you can use left multiplication to take vectors that are tangent to the identity. You can push them to vectors that are tangent to whatever point you want just by left multiplication. Um, are there any questions on this? Okay. Um, but this you can do better for matrix groups. This is because we know how to like actually differentiate like matrix valued functions. So let gamma be from some interval into SLNR be a curve such that um, gamma of 0 is the identity and gamma prime of 0 is x. Okay. Um, so in other words, what I mean is uh, x is equal to d by dt at t equals 0 of gamma of t. Then consider psi from I into S ln r given by psi of t equal b times gamma of t. Okay. Then psi of 0 is equal to b and psi prime um, psi prime of 0 is equal to d by dt t equals 0 b gamma t is equal to b gamma prime at 0, but that's just equal to bx. Okay. So another way of looking at this space is all you do is so this should sort of convince you that the derivative of left multiplication is just left multiplication again. Okay, so multiplying on the left by a matrix, the derivative of this is just again multiplying the tangent vector by the same matrix. So, this shows that DLB can be thought of as LB. I mean, it makes sense, I think, because both of these maps are, linear, and so I mean, all this shows is that these maps are actually the same, because if the tangent space at identity is just the image, sorry, the tangent space at any point is just the image, and you showed that you can get to that image by using left multiplication, that tells you that both of these are actually the same map. Um, okay. So what this means is that the tangent space at some arbitrary point is just obtained by taking x, um, by taking bx for x for the trace of x being 0. And now an exercise, so exercise, show that um, TB, SL, and R is also equal to XB, where X, the trace of X is 0. When I say equal, I actually mean isomorphic. Um, so yeah, again, it's a similar computation to what we've done here. Um, are there any questions? Okay. So with this out of the way, let's now talk about what I think is actually one of the most important constructions in at least, early geometry. Um, Okay. Um, and that's of, you know, bu vector bundles, like examples of vector bundles. Um, so let me, um, but not only any vector bundles, but, you know, vector bundles that are somewhat associated to the tangent bundle. Um, and yeah, okay. So let's see this. So if you recall, we last time I think we sorry, before the break, I think we talked about how you can take a vector bundle and then look at representations and then, define new vector bundles with a similar structure. So let's start with the cotangent bundle. Okay, and let us start with the cotangent bundle. Um, and if you, so what does this mean? So its fibers, um, its fibers at each point will be the tangent space, the cotangent space, which is this, and this is nothing but the dual space of the tangent space. Okay. Um, okay. Are there any questions on this? Because I think this is a very important thing to know. So, we're following a similar construction to what we did with the tangent bundle, where we took the fibers to be, the tangent spaces, and then we, we required some gluing conditions, and once we had those gluing conditions like satisfied, we could glue the thing together and get a manifold on its own that sort of sits, that allows M to sit in it with some natural projection maps like onto it, because and then it satisfied some other properties such as like a co-cycle condition and so on and so forth. So now we're doing a similar, we're doing like a similar sort of construction. Um, so before we actually even construct this, it's like the first question is, why would someone care about this? Right? Like, why does anyone even care? And the idea is simple. So suppose f was a function from M into R, smooth. Right? We've already seen this sort of construction show up a bunch of times, and one of the main places that we've seen it so far was the regular level set theorem, right? Um, then what I want you to note is that if I take the differential, which was again something that was important, is a map from the tangent space at M into the tangent space at the image, right? But this thing is just equal to R, right? What this tells me is that df of P is actually in the cotangent space, right? Because it's a linear map from my vector space into the field. So it's actually a map in the um, dual space. Okay. Um, and this is why we like mainly care about the cotangent bundle, is because of, um, a lot of constructions used the notion of a cotangent bundle. Um, and once we have the cotangent bundle, we'll see how it allows us to generalize many things, such as integration, which we will also talk about very soon. Okay. So, okay, are there any questions so far? Like on the motivation for why we care about the cotangent bundle and so on and so forth. Okay. Um, One thing to note also is that we will see um, that if you have some configuration space, okay, um, a natural way to, talk about dynamics of particles is using the Hamiltonian formalism of classical mechanics. Um, which if you haven't seen, please let me know. Because like all the constructions that we will talk about when we start talking about like symplectic geometry will relate to Hamiltonian dynamics. So if you haven't seen Hamiltonian dynamics, let me know. I'll we one meeting we can talk about Hamiltonian dynamics in the usual way. But please let me know. Um, so it turns out that mathematically speaking, at least, we can encode information about Hamiltonian dynamics on the phase space. And it turns out that the phase space is just the cotangent bundle of the configuration space. Okay. Um, Moreover, we'll see later on that the cotangent bundle actually has a canonical choice of something called a symplectic form that allows us to talk about dynamics. So that's another, motivation for why we care about the cotangent bundle from like a physics standpoint. Okay. So let me let's now talk a bit about how the like tangent bundle was sort of defined. But actually, let me write this down. So, um, if we have some configuration space M, then we care about T star M since it is the phase space, and hence we can talk about Hamiltonian dynamics. Hamiltonian dynamics. Okay. Okay. So let's now look at the tangent bundle, and let's you know um try to dualize the idea of a tangent bundle. So start with some it's okay, we already have some manifold M, and now start with the chart um U phi around P and M. Okay. Then we have a basis for TPM given by if you recall, this is partial xi at P is nothing but d phi inverse at phi inverse of P of partial um, yi at P, where partial yi at P is the standard basis for TPRN, TPRN, or TPRM, I guess. Um, there should be T phi of P. Okay. Um, okay. So now what we're going to do is we're going to define these one forms. Sorry, not one form. Shouldn't call it that. We'll define the dual vectors of this basis. Okay. So we'll define the dual vectors. So now we define the dual vectors, and we'll call them dx. Okay. At I at the point P, um, and they'll be in TP star M such that dxi at P of partial x j at P is just delta ij. Okay. All I've done is I've defined the dual basis and I've called it, dx. Um, One thing that I will now allude to is if you've ever done integration, you know that you use like dx as, to indicate what variable you're in, integrating with respect to. Um, and it looks pretty similar to this. Um, so from a geometric standpoint, we'll actually see that these are actually useful. Like these cotangent objects are sort of what we want to integrate. Okay, and that's another use they have. It's something we want to integrate. Um, okay. One thing to note about this is that dxi at p is nothing but um, uh, d of pi I composed with phi at the point P. So you take your chart, you map it over, and then you project down. And d of x is just the differential of this map. This is an exercise. So check this. Um, Again, it is enough to show that it holds on the basis. That if you can show it on the basis, you've shown it everywhere. Okay. Now, the main defining property of the tangent bundle was not only that its fibers are the tangent spaces, but also how does this structure interact in a change of coordinates, right? So what we're gonna do now is let v psi be another chart around P, okay? With basis tangent vectors, um, partial y, partial x tilde I at P, given by d psi inverse at psi of P, partial yi at psi of P. Yeah. This should not be sub pi psi inverse. Sorry, phi inverse should be like that. Okay. And now the question is, okay, the tangent bundle, the main topology of the tangent bundle, or the main defining characteristic of the tangent bundle, like I've said, is by how these two things must interact. Okay, is how is this basis related to this basis? That is the main question. Um, so partial x I at P is equal to d of phi inverse of partial of phi at P of you know the usual. Um, and now the idea is I'm going to use chain rule. Okay. Um, I'm going to sub in an identity in here. I'm going to force it in and then just see what the computation leads me to. So I'm going to do d of psi inverse compose compose phi inverse at phi of p. And this is going to be, now I use chain rule. So it's going to be this. And now, okay, so phi of p maps by phi into p and then by psi into psi of p. Yeah. Of d of psi compose phi inverse at phi of p partial yi at phi of p. And if you remember, this is the transition function, right? This right here is the transition function. And so, okay, this sort of tells us that we're moving in the right direction, right? Like this is how we um, want to go. Uh, and then this is this d of psi inverse psi of p. Um, and then this should give you partial x tilde I, sorry, x tilde j, partial x I um, at phi of p times partial x. Wait, I think this should be a y. Sorry, wait, I made a computational mistake somewhere. Hmm. Okay, you know what? I will not worry about this too much, and I'll just give you the final answer. You should get this. Um, and it's an exercise to show, it's an exercise to compute this computation. So exercise, fill in the steps. Um, it is just a computation in, matrix multiplication, basically. Um, but okay. So what this tells us is this tells us that tells us that partial x tilde um sorry, x of I is I'll omit the at the point and whatever and just write it like this. So x tilde j partial xi partial x tilde j, or in other words, this map must be invertible because this is just the Jacobian of the transition matrix. This is the Jacobian of the transition function. So inverting this gives us partial x tilde j is nothing but partial xi by partial x tilde j partial xi. Yeah. So and then this, right, this matrix prefactor that we get is the defining property of the tangent vector, right? In other words, physicists would say that a tangent vector is something that transforms like a vector. And this is what they mean. They mean that something is a vector only if, when I do a change of coordinates, I all I have to do is I have to multiply by a change of basis matrix. Okay, that's what physicists mean by a vector is something that transforms like a vector, or a tensor is something that transforms like a tensor. Okay, this is all they. Under a change of coordinates, you just multiply by a change of basis matrix. Okay, so now if we want to dualize this, right? The obvious way would be a covector or a dual vector is something that transforms by the inverse, uh, in a way that is inverse to that of a vector, right? So let's do the computation out and see that what should we expect from dual vectors. So let omega have components omega I dxi in some basis. And let it so this omega p here, um, and then let this be a function of p. Um, let's write it like this. Okay, so it's something in the dual space at the point. It has some coefficients. Oh my God, why does it keep changing it? It has some coefficients omega I in the basis given by phi, but it also has components omega tilde given in the tilde coordinates, right? Because again, these are two valid coordinates. And now let's see what the relationship between omega I and omega tilde of I is. So note that omega I, right, is nothing but omega j of dxj evaluated at this. And this is nothing but omega evaluated at this tangent vector. But this is nothing but omega tilde I, um, evaluated at dx tilde I. Sorry, this should be j here. Sorry, j at p of partial x tilde I partial x I partial x tilde. That should be a k. That should be a k at the point P. And then this thing is just constant. So you have this like dual vector acting on this basis vector, which means that J must equal K. So in other words, we have omega J tilde times this prefactor times delta JK, um, which just simplifies down. So okay, J equals K. So that means this must be a J, right? So this whole thing is replaced by omega tilde J partial J partial X. Okay. Um, okay. Are there any questions about this computation? Hmm? Okay. One second, sorry. Okay, so and now if we look at how these are laid out. So um so in this case, okay. So now there's actually something that you need to be a little careful about, right? Because you might tell me, okay, I thought we were um talking about the fact that dual vector should transform as the dual. But if you look up here, right, it seems as though the like the compo this thing has transformed the same way as a tangent vector. Look, what I mean by that is this is in in this basis, um, this is in this basis, and then we have the same change of basis matrix in front. Right? So what this tells you is that the components transform as vectors, which means that for them to be, you know, um, for it to be consistent, we need that the like dual vector itself, um, that the dual vector itself transforms by the inverse. Right? This is a similar logic we applied when we started talking about, in linear algebra. Um, like when we talked about like the same change of basis stuff in linear algebra, where the components of the dual vector transform as the like vector itself, and the like dual vector itself transforms as the component of the vector, right? Um, so that's what's going on here. So this means that dxi at p is nothing but partial xi partial xj dx tilde j at p. Okay. And that just comes out directly. Like if you plug this in here and here, you'll see what I mean. Uh, okay. Are we happy with the fact that like tangent vectors and their duals transform dually? One transforms by the Jacobian, one transforms by the inverse of the Jacobian. Are we happy with that? Okay. So this is now this is the defining characteristic of the cotangent bundle. It's something that is associated to the tangent bundle in the sense that if I have some transformation law, I can take its dual transformation law, right, and get a like the dual vector bundle, which is basically what we're doing here. Okay, so that's the entire point. So now remember the way we defined vector bundles by was first we need a collection of sets, then we need to paste them, And then we need to give some like co-cycle, representation or whatnot. Um, so let's now work towards that. Um, so let so now I'll call this defining the cotangent bundle. Okay. So let U phi be an atlas on M. Okay. U phi, okay, be an atlas on M. Uh, then let V alpha just be phi alpha inverse of U alpha. And, I mean, this is very similar to how we defined the tangent bundle. So so far so good. So I mean, again, we started with um, the same initial data as the tangent bundle, and the only difference is going to be um, what the representation we're going to use is. Okay. So um, then the cocycle defining Tm was G alpha beta from um, U alpha U beta into GL MR um, given by G beta alpha of a point X was nothing but D psi beta alpha composed with phi alpha. And we see this because, I mean, um, this is what this matrix is here. This is the derivative of the transition matrix evaluated um, at the point phi of p. Yeah. Okay, so are there any questions? I mean, again, we talked about this construction, but still, are there any like questions regarding like this construction and why it like defines a tangent bundle or why it defines the tangent bundle, I suppose. Okay. Okay, so now the idea with associated bundles is going to be very simple. We're going to take, the same data, and now we're going to look at representations of this space, and all we're going to do is we're going to move it, because what a representation will do is you know, um, it'll give us like a huge family of things that will like similarly define cotangent, um, co-cycle conditions. So now we look for a representation um rho from GL and R. And for now we look at GL like LR for some L. Okay. Then we get cocycles rho composed with G beta thing equal T beta alpha. And now we have an exercise here. Check that T beta alpha satisfies the cocycle condition. If okay, and now in the case of the cotangent bundle, we clearly see that this representation should be the dual representation. So for the cotangent bundle, rho is going to take so rho of A is going to be a dual inverse. Because remember, we have to dualize, but then for it to be representation, we have to take the inverse. Okay. Then pasting, um, then doing a similar construction as Tm, we define T star M. Okay. I mean, if you want, you can recap the construction we did a couple like lectures or like couple meetings ago about how you take a cocycle and make it into um you make it into a vector bundle. Okay. So in any chart, U phi, we can write omega in T star M as um omega I dxi, um where omega at P, where omega I is in R, um, and dxi at P are the duals of partial xi. Um, okay, so now remember can someone remind me, did we talk about vector fields, like what a vector field was? I forget.
I think
I
so.
Okay, so I mean, I'll just define them again. So just in case, because I think one of you remembers me doing it, one of you doesn't. So
I might also just know it from like other stuff and think it was here, but
okay, I see. So yeah, I mean, just for like, completeness, I'll talk about it. So the idea with a vector field, I mean, is very simple. At each point, you want a tangent vector. Okay. So a vector field, the idea is simple. The idea is that to each point, associate uh, a tangent vector. Okay. Yeah, that's all there is to it. Um, so these are called sections. So definition, I'll give a proper definition this time. A section, um, sigma of a surjection pi, okay, is a right inverse. So in other words, this means that pi composed with sigma is just the identity. Um, and then vector fields are sections of Tm. I mean, the idea of a section is that you take whatever is being surjectively mapped onto, and then you like put it into uh like the overarching space, and you get a section of this entire space um that is like identified with this. Um, so the space of smooth sections, so a smooth section. Wait, I don't want to word this. So a vector field is smooth um, if, so I guess let me write it this way. So vector field X from M into Tm. So a priori, vector fields may not be smooth, they may not even be continuous. Um, Again, we can talk about the continuity of a vector field by looking at if it's continuous from a map from here to here. But we can also talk about it in terms of coordinates. So, I mean, we can talk about it in terms of coordinates, but another way to talk about it is a vector field is smooth if for all f in C infinity m, x of f from m into r, um, yeah, is smooth. Okay, so remember, and I guess x of f at a point P is defined to be x at the point P at f, right? So this is the derivative of f in the direction of x of P. Okay. Um, we denote this space of smooth vector fields on M by this math frac. So this is like math frac x. Okay, so are there any questions about like what a vector field is and what a smooth vector field is? Okay. Um, in general, if we have smooth vector bundle, right? Then its space of section, the space of sections is denoted by like this. Okay. But in the case of, uh, vector fields, we call it this, but in general, it'll be called this. So in other words, like, so you have this is actually equal to this of t. Um, okay. Uh, smooth sections of t star m, I'll call this omega 1 of m, are called smooth, actually they're called differential one forms. Okay, so we have finally introduced the notion of a differential form. And all a differential form is, like a one form, all it is at each point, you associate a covector in a way that is smooth. Okay. Are there any questions about what one forms are? Okay. Um, okay. Um, now, just to be pedantic, I want to mention something. Um, so, M cross R into M is a, vector bundle. And so it has a space of sections. Um, and this space of sections is precisely functions from M into R, right? You can think of this as so. Hence, the space of sections, smooth sections, is equal to the space of smooth functions. Or I guess you can like identify it, but you can also call it equal. And for this reason, we'll also call this space omega 0 of M. So in other words, the space of differential zero forms are just, smooth functions on M. Um, are there any questions? Okay. Um, one thing to note, so note, omega is, a smooth one form if and only if for all x in this, um, we have um, omega x defined by omega x at the point P equals omega p of xp is smooth. Um, and you can check that in local coordinates. What this means is that, the component functions are smooth. Okay, so this is what these are what differential forms are. So, I mean, this is what a differential one form is. Um, I did want to talk about differential like forms in general, but I think that might take too much time. Um, so what I will do is we can talk about it like on Tuesday, um, if that's okay with you guys. Is that fine? Okay, I guess I'll take that as a yes. Um, so, okay, um, I mean that's it for the content for today. Are there any questions like regarding anything we've done? Okay. If there are not any questions, I guess I will see you guys on Tuesday.